Good evening. Thanks for joining. Okay. So, good evening, everyone. Let me start the session. Let me start with a small brief introduction. Mm, this is Saravanan, Prime Minister Research Fellow and Research Scholar of Department of Civil Engineering from NIT Tiruchirappalli. So, this is the PMR of TA-ship problem solving session for the course, NPTEL course, wastewater treatment and recycling. We are in the week 7 of 12-week course. So I am taking this course as a part of PMR of TA-ship. So every week, Monday, 6 to 8 is my session. And other two scholars are also parallelly taking in on Saturday and Tuesday, 6 to 8 p.m. So you can also attend their course, their sessions as well. And our other session will be of 2 hours. First 1 hour we are going to discuss the same lecture material what sir has discussed in the YouTube videos, and other 1 hour we are going to discuss the older assignment problems that how it will work. Okay. So all the course materials are from Dr. Manoj Kumar Tiwari sir of IIT Kanpur, and all credits goes to him. Yeah. Let me start the session. So first week of this course we have discussed about the wastewater treatment and recycling definition. So why we need to treat the wastewater? We are getting water, we are treating and we are drinking, or we are using. After usage, what we can do with the wastewater, that's what we have discussed. If we are not treating, what will happen and all we have discussed in the first week. In the second week, we need to know how much we are going to treat and what we are going to treat. So how much quantification based on the population for the future we have estimated in the second week. In the third week, we have discussed about what is the characteristics of the wastewater. Without knowing the characteristics of the wastewater, we can't treat the water, right? So we had the quantitative and qualitative assessment of wastewater. In the fourth week, we have discussed the yeah, let me admit others. So in the fourth week, we have discussed about what are the problems if you are not treat the wastewater, and what are the statistics, global and Indian statistics of wastewater production. Then in the fifth week, we have discussed about the preliminary wastewater treatment that consists of bar screen, that is screening, um, followed by grid chamber, followed by plain sedimentation. In the 6th week, we have discussed about the secondary treatment, with that is the aerobic treatment of wastewater by activated sludge process, that is ASP. We had a so in the last week we have discussed about the ASP. We had a activated sludge tank, that is the aeration tank, followed by the secondary sedimentation tank. So we have treated most of the constituents of our wastewater, such as, let me take our pen. Like, uh, yeah. So any wastewater contains suspended inorganic matter, suspended organic matter, dissolved inorganic matter, dissolved organic matter. So the first step, preliminary treatment, in the screening, all the inorganic matters, bulk matters are deposited. Any inorganic or organic bulk matters got deposited, like wood, textile, cloth, plastics and all will be removed. Followed by grid chamber. Grid chamber removed all the inorganic solids. Then followed by plain sedimentation. Here all the organics will be settled, primary settling tank. Okay. Then we gone with the ASP treatment plant, where a tank was there along with the secondary settling tank was there. So here aeration will happen. So here all the soluble organic matter got removed. Only left over is soluble inorganic matter, like salts and all, will be removed in the tertiary treatment, that we will see in the upcoming session. So last week what we have discussed is this aerobic treatment of wastewater for the soluble organic matter. This week we are going to see a simple topic called anaerobic treatment of wastewater. What is the difference between aerobic and anaerobic? Aerobic treatment will use the oxygen for the survival of microorganism, and the microorganism will degrade the organic matter in the wastewater. So organic matter will be the food, microorganism will be the organic that major role player, and if it acts upon the organic matter and it will break down into simpler compound, it will assimilate for the cell growth and energy will be produced. That energy will be taken care by the microorganism. So this breakdown is called the catabolism. The production of energy on its own cell mass is called anabolism. The whole process is called metabolism. That's what we have discussed in the last week. So during this process, whether oxygen is required or not, that is called aerobic or anaerobic process. If the oxygen is required, then that type of microorganisms are called aerobic microorganism. If they are treating the organic matter without the oxygen, that is the without free available oxygen, but it will use oxygen from molecular bound compounds like sulfates, nitrates, um, carbon dioxide, or any organic matter containing oxygen. So this type of molecular bound oxygen will be utilized by the microorganism. Then it is called anaerobic microorganism. Anaerobes. That treatment process is called anaerobic treatment of wastewater. You got it. So here, why we are shifting from aerobic to anaerobic? Which condition aerobic will be good? Which condition anaerobic will be good? Because see, organic matter, when it is acted upon by anaerobic microorganism, it will produce, aerobic microorganism will produce only CO2. All the organic matter will be converted into, organic matter means C, H and O will be there. That will be converted into CO2 plus H2O in aerobic treatment process. But in anaerobic treatment process, all the organic matter will be converted into methane and carbon dioxide. Why? There is no much oxygen, so there is no oxidation of carbon. Only some part will be oxidized into CO2, others will be reduced to methane. So here reduction is happening. So anaerobic treatment is a collection of biological process by which microorganisms break down the organic matter into methane and carbon dioxide in the absence of oxygen. That is what very important. Okay, so the most of the organic carbon is converted into biogas. So this combination of methane plus CO2 is called biogas. You got it. The gas that is produced from waste is called biogas. Okay, while little goes into the sludge production. But if you see in the organic aerobic treatment, mostly sludge formation will be there. Little will be converted into CO2 and H2O. But here, most of them will be converted into biogas and little sludge will be produced. So treatment of sludge cost will be reduced. That is the advantages of anaerobic treatment process. See this material flow chart, you will get a broad idea. Here we are in aerobic process, we have a aeration tank followed by a settling tank, right? So in the aeration tank we need to supply air. we need to supply oxygen or air. So air supply is required. That is expensive. But in anaerobic system, no requirement of oxygen. So there is no aeration. So that cost will be reduced. See, 100% of organic matter, out of 100% of organic matter, 45 will be converted into carbon dioxide into water vapor, CO2 plus H2O, and 10% will be going with the effluent. 45% will be converted into sludge. But in anaerobic treatment, out of 100%, 80% will be converted into biogas. That is CO2 plus H2O. Out of 100% biogas, 70% will be methane, 30% will be CO2. You got it. If I am getting 100 kg of biogas, 70 kg will be I mean percentage, in terms of percentage I'm saying, 70% will be methane, 30% will be CO2. So out of 100% organic matter, 80% is converted into biogas, 15% is going out with the effluent, because here treatment efficiency will be less. But only 5% is the sludge production. Think about 10,000 kg milligram per liter of COD, or 1 lakh milligram per liter of COD. If I am using aerobic treatment, 50%, nearly 50% is 5,000 milligram per liter will be sludge. But here only 500 will be my sludge. You got it. So I am reducing the sludge treatment cost to around 40% reduction. So that is a big a benefit of anaerobic process. And I am getting 80% as methane. So if I am treating 100 kg of COD, 80 kg will be my biogas. So out of that I will mass calculate and calculate the methane production. So that is again a valuable gas I am getting as an energy source. Okay, see the same diagram. 100 kg BOD, carbon dioxide and water vapor will be there. Biomass will be like 45%. Along with that, we need a aeration of 60 kilowatt. That is the energy requirement. But in anaerobic treatment process, if you give 100 kg, 80% will be the biogas. Out of that, 75% will be my methane. You got it. Out of the 80%, 70% will be 75% will be methane. 25% will be carbon dioxide. Whereas 15 kg will go with the effluent, and 5% will be my sludge. That is a very little amount. If you think in a numerical point of view, 1 kg of COD, 0.35 Newton meter cube of, normal meter cube of methane will be produced. That is 3.8 kilowatt of energy. Instead of giving energy, I am producing energy. You got the difference. So that is the difference from aerobic to anaerobic. A similar way will be followed in solid waste also. In biogas plant, I am feeding all the food waste, mess waste, in a digester, anaerobic digester. In many of the colleges, you might have seen a biogas generator, like this dome kind of structure. I will feed all the waste here. It will be closed. There is no oxygen entry. Biogas will be taken out, and that will be used for energy production. You got it. So that's the advantage here. What are the advantage and disadvantages of anaerobic treatment system? Low production of solids or sludge. That is the first advantage. 5 times lower than the aerobic process. Because there 50, here only 5. Sorry, 45, 5. So that is 5 times lower than the aerobic process. Low energy requirement, no aeration is required. Low land requirement, because I don't want aeration tank, I don't want a settling tank. All will be done in the anaerobic system itself. Low construction cost. Production of methane, that is a high calorific value gas. So I will get energy. Possibility of preservation of the biomass, because I'm not wasting any sludge. Whatever the sludge there, that will be taken care inside itself. So preservation of biomass, long HRT, sludge retention time. Organic load. You can treat 1 lakh milligram per liter COD, 10,000 milligram per liter COD, but anaerobic system low organic load, like normal municipal solid waste and all will have low organic weight. Lots of water will be mixed. So low strength wastewater, anaerobic process will not work. Why? Because already the bacteria will get less food only. We are not giving oxygen also. So it will only act with the large organic matter system only. Okay, you got it. And low nutrient consumption. Application in small and large scale plants. But the problem is susceptible to inhibition. Lots of factor will affect the anaerobic system. That's what we are going to see in the upcoming slides. Startup issue. Initially, all the microorganisms should need to settle for the system or adapt for the system. So there is a startup issue. After startup for some time, it will pick up. Then post treatment of methane what we are producing. We can't use the biogas as it is. We have to extract methane out of it. CH4, CO2, H2S, all gases will be there. I have to remove H2S from the system. So we need a post treatment to use the biogas. And biochemistry and microbiology of anaerobic systems are complex, not like aerobic system. We can't frame equations like aerobic system. So that is a complex biochemistry involved in that. And possibly generation of bad adults, like as I mentioned, some anaerobic digester, if you go nearby, some smell will come. So other problem is the major issue if it is not properly maintained. And generation of effluent, because we are um, getting uh, like effluent which have a 15% like residual concentration. I am supplying 100 kg of COD, 15 kg of COD will come out. So that is another problem. But there only 5% will come out aerobic. So that is another problem. But think about the higher organic loading, right? 1 lakh, only 15,000 will come out. So that is a good reduction. Okay. Then unsatisfactory removal of nitrogen, phosphorus, and pathogens. So nitrogen pathogens, sorry, phosphorus and pathogen, this type of nutrient will be removed with the aerobic system only. With the high retention time, more supply of oxygen, it will remove first CBOD, then nitrogenous BOD. So there are two types of BOD, right? In a system with the time, first BOD will be NCBOD, then NBOD will be there. So nitrogenous BOD will also be removed with the large supply of oxygen for long time. But here anaerobic system, this type of nutrients like NPK will not be, and pathogens will not be removed. But this anaerobic treatment system is getting popular. If you think about 1970 to 1980, there is no increment in the anaerobic treatment system. But after 1985, you see a drastic increase in the number of plant constructed. So because there is a less requirement of an area, less operation and maintenance, and energy is produced for free of cost. After 1980s, all countries are going towards energy. So renewable, this kind of renewable energy. So that's getting popular. Now you think about the process of anaerobic degradation. Like how aerobic degradation works. Uh, Organic matter will be there, oxygen will be supplied, microorganism will break down with proper temperature, proper pressure, proper retention time, sludge retention time, proper organic loading rate, all this food to microorganism ratio, oxygen supply rate, all if you maintain, then carbon dioxide and water will be produced, plus some new cells will be formed. That new cells will be settled in the secondary settling tank. So this is how aerobic system will work. But how anaerobic system will work? What is the process behind that? There are four major steps in the anaerobic degradation of organic matter. What is the first step? That is hydrolysis, acidogenesis, acetogenesis, methanogenesis. So it will be very simple if you see the process. Initially, all the higher molecular organic compound, high molecular weight organic matter will be added with water, or the process will utilize water to convert into low molecular weight organic matter, because microorganism will not degrade all the organic matter. So some enzymes it will produce, that enzyme will convert the high molecular weight or high fatty acids into low fatty acids, low molecular. This process is called hydrolysis. uh, Okay, so let me continue. So this process is called hydrolysis. Then this lower molecular weight organic matter will be converted into acetic acid, or acids, volatile fatty acids, because acids will be the precursor for methane. So all will be converted into volatile fatty acid. This process is called acidogenesis. Conversion into acids is called acidogenesis. The name itself, it's mentioned acid is forming. Hydrolysis, we are using water, so hydrolysis. Then all the volatile fatty acid will be converted into acetic acid, that is CH3COOH will be produced, or acetates. That's why it's called acetogenesis. Acetates are produced, so acetogenesis. This is also acid, but all acids will be converted into acetic acid, so acetogenesis. Then from the acetic acid, methane, CO2 will be produced. So that is called methanogenesis. Methane formation is called methanogenesis. What is forming? Based on that, we are giving the name. Catalyzing water, hydrolysis. From high molecular weight converted into low molecular weight. Low molecular weights are converted into volatile fatty acids called acidogenesis, because acids are forming. Then acetates are forming, so acetogenesis. Then methanes are forming, so methanogenesis. So four stages of anaerobic degradation. You got it. So hydrolysis, you converts high molecular compound into compound suitable for energy production. Then acidogenesis, conversion of hydrolyzed compound, that is the lower molecular weight. That is the hydrolyzed compound into identifiable lower molecular weight compounds like volatile fatty acids. That is the intermediate compound. Then acetogenesis, that converts long chain fatty acids. These are all long chain fatty acids converted into um, hydrogen and acetate. H2 will also be produced. Okay, so that process utilizes acetogens. So what are the bacteria involved in this? They will have a name. So this process will require acetogens. Then from the hydrogen and acetate, methane and CO2, that is the biogas will be produced. That is methanogenesis. The bacteria involved are called the methanogens. You got it, the methanogens. That is the bacteria involved. So these are the four stages of anaerobic degradation: hydrolysis, acidogenesis, acetogenesis, methanogenesis. Okay. Yeah. Now, what is happening in this steps? What are the bacteria involved in these steps? So, long chain, or high molecular weight organic matters like protein, carbohydrate, lipids are converted into amino acids and sugar that are low molecular weight fatty acids. So, that process is called hydrolysis. Is correct. So, what is the bacteria involved in this? Hydrolytic and fermentative bacteria. Hydrolytic and fermentative bacteria. Okay. So after amino acids and sugar and fatty acids will be converted into um, like the volatile fatty acids. That process is called acidogenesis. What will be used in this? So that is the fermentation process. Same fermentative bacteria will happen and converted into acids. After this acid will be converted into acetic acid. So that same microorganism will be using fermentative bacteria, but converting them into acetate and hydrogen, and the same will be transforming again and again acetate to carbon dioxide to acetate. This exchange will happen with the homoacetogenic bacteria. This will happen with the acetogenic bacteria. Okay, you got it. Then this methane production will be with the methanogens or hydrogenotropic methanogens. There are two types of methanogens. From the acetic acid methanes are produced, then it is called acetic-lastic methanogens. From hydrogen and carbon dioxide, if methane is formed, then it is called hydrogenotropic methanogens. You got it? So I will erase and tell you again. This may be confusing. Yeah. So high molecular weight organic matter converted to low molecular weight organic matter by hydrolysis. The bacteria involved are called hydrolytic bacteria or fermentative bacteria that converts into uh, volatile fatty acids. So this volatile fatty acids are converted into acetates by acetogenic bacteria and hydrogen to carbon. Both will be the product. Okay. Then acetate, when it is converted into methane, then it is called acetoclastic methanogens. When hydrogen and the carbon dioxide H2 plus CO2 convert into CH4, then this process is governed by hydrogenatotropic methanogens. Okay. Yeah. So again, if I am splitting the process, hydrolysis, see, long high molecular weight organic compound will have all ORs. So that will be converted into OH. Alcohols are produced, glycerols. The enzyme reacted in this specific equations are lipase. How this is happening? With the addition of water and production of enzyme by the bacteria. So bacteria unable to take a particular organic matter. So it will excrete the enzyme that converts the complex undissolved organic matter into less complex dissolved compounds. After it get dissolved, the bacteria can easily act upon and it can produce the methane. So the process is very sensitive to temperature and temperature fluctuation. So every process requires a separate temperature, and this hydrolysis process is the rate limiting step in the whole anaerobic digestion system. What is rate limiting step? Any process will have different steps, out of which takes longer time are called rate limiting step. Like aerobic treatment will require aeration followed by sedimentation. So there are two steps involved in it. But anaerobic degradation process requires hydrolysis, acidogenesis, acetogenesis, methanogenesis. In this, hydrolysis takes a longer time. Other three processes will take less time to make the product. So which takes the longer time are called rate limiting step. So hydrolysis is the rate limiting step of anaerobic digestion process. It converts OR into OH in the presence of water and enzymes. You got it? Yeah. Then whatever the produced OH will be converted into volatile fatty acids. That is called acidogenesis. Volatile COO dash, that is the volatile fatty acids. Whatever that will be there, that will be converted into acid form. Organic matter will be converted into acid forms. That will have a Gibbs free energy because everything requires energy that will produce some energy. This is negative, so that is producing energy. If I am supplying energy, that will be del G plus. And if the Gibbs free energy is negative, then it is generating energy, right? Then acidogenesis reaction that requires uh, converting this COO into, see, all are converted into acetic acid, CH3COO. Whatever the acid, volatile fatty acid, that is converted into acetic acid or acetate. Both are same, acetic acid. CH3COOH or H or something minus. Right? The H plus is here. All this process will produce H plus and CO2. That is all reducing the pH of the system. That's why all become acidic. Okay, all are related to acid. So the pH of the system will be in acidic range. So now OR converted into OH, then OH converted into COO minus, volatile fatty acids, then acids converted into acetic acid, CS3COO minus. Finally, whatever the acetic acid I am having, that will be converted into methane is one step. Or whatever the hydrogen and CO2 I am getting, that will have a reaction and CH4 will form. Some more reactions are there. See, directly from the uh, system, amino acids, some methanes may form. That is called alcohol to methane production, or acetic acid to methane production, or directly CO to H2O will form methane, or acetic acid may react with the sulfate, nitrate and form uh, this compounds. That is the extra biogas contains CH4, CO2 and small trace amount of H2S and ammonia. These are all harmful because ammonia, it will also take all the acetic acids, right? So that is the problem. So if a system contains sulfates and nitrates, that will produce H2S gas and ammonia gas. That is inhibitors for the reaction, right? See, all are producing energy. For this conversion, some group of methanogens will happen. For another group of reaction, another type of methanogens, because all are methane formers. Methane formers are classified into acetotrophic and hydrogenotrophic. That are all methanogens only. Acetotrophic methanogens will convert acetate into methane. Hydrogenotrophic methanogens will convert hydrogen into methane. You got it. See here, it is a very important diagram. Substrate concentration and mu. For aerobic treatment also we have created a substrate utilization rate and substrate concentration. Substrate is the food. Okay, substrate concentration. If the substrate concentration is more, then this bacteria will be acting. If the substrate concentration is less, wait. See, so at the lower substrate concentration, my growth rate is high for this type of bacteria. If I am having more organic matter, then I will use this microorganism to uh, give a good yield of biogas. So based on the concentration of inlet COD, I can fix the system. I can supply that microorganism alone. Okay, then the system will work better. Yeah. See, which organic matter will be removed? Why we are concerning about COD in anaerobic system and BOD in aerobic system? Because aerobic treatment will degrade microorganism in the presence of oxygen, but anaerobic treatment system will not use any oxygen. So, if you take BOD as a measuring parameter, then BOD is again measured with the supply of oxygen for 5 days, right? So that is the problem. Aerated water we are supplying to find the BOD. So BOD will not give a good measurement. That's why I am using COD in the absence of oxygen. I mean oxidation only, but chemically oxidizing the organic matter in the system. So that COD value will be reliable for anaerobic treatment system measurement. So all the COD will be classified into two types. One is soluble, another one is insoluble COD. So if you think about soluble COD, that will have mostly biodegradable organic matter. But insoluble COD will contain particulate matter as well as cell mass. Cell mass is the bacteria. You got it. So which will be removed from the system, which will not be removed from the system. So total COD will be classified into recalcitrant and biodegradable COD, which is not biodegradable like small type of microplastics. Microplastics are organics, but all the plastics are organic but non-biodegradable. So that are all recalcitrant, will not work with the biological system. So that will be coming out with the system. But treated in the systems are biodegradable. All the biodegradable will be converted into some bacteria cell mass, and some will be converted into volatile fatty acids. All the among all the volatile fatty acids, some will be converted into methane, some will be present in the system. So which will come out? All the microorganisms will come out, all the methanes will come out. But along with the effluent, recalcitrant will go, and remaining volatile fatty acids will go with the effluent. You got the system? All the COD will be classified into recalcitrant and biodegradable, which are non-biodegradable or recalcitrant. Okay, then biodegradable will be converted into cell mass by the bacteria, like biological reactions, and some will be converted into volatile fatty acids. Again, by reaction, it will be converted into methane. Some will resist formation of methane. So that resisted volatile fatty acids and recalcitrant pollutant will come out along with the effluent, and cell mass and methane will be taken out of the system. So that is the total COD removed. Yes. So what are the factors affecting anaerobic digestion? As I mentioned, there are a lot of inhibiting factors. Like this system is very sensible to the environment. If small slight pH change, a slight temperature change, whole system will fail, and nothing, no more biodegradation will happen. So that is the problem. So first factor is time. Assimilation of the microbes to a substrate will take 3 to 8 weeks. So that's why the anaerobic system we are feeding very slowly. It is taking long time to treat the organic matter. But in aerobic, if you supply oxygen, it will treat, and it is a continuous system. And greater stability towards stress-inducing events like hydraulic overloads, fluctuations in the temperature, volatile acids, ammonia concentration. Based on all this, the time will vary. So mostly it will take a longer time, 3 to 8 weeks. But in the aerobic system, it will be in terms of hours and days. You got it. But time will be more for anaerobic system. Then pH, acidity and alkalinity, if you see, the optimum pH required for the methanogens is 6.6 to 7.6. Otherwise, it will not work. But my system produced more acids, more H plus ion, CO2, so that reduces the pH to acidic system. So I will add some buffer to make it into 6.6 to 7.6. Then only methane will form. All the steps, as I mentioned, 4 steps are there. Methanogens will not work with the acid pH. So I want to make it into like neutral pH to make the methanogens to work. As I will see, methanogens will work only with 5 to 8.5. If the pH is less than 5, methanogens will not work. pH decreases in the formation of volatile fatty acids. So I have to add a buffering agent like ammonium bicarbonate, calcium carbonate need to be added to maintain the pH in a desirable range of 5.5 to 8.5. Then temperature, as I mentioned, like 30 to 40. What is the range of microbes will survive here? Mesophilic bacteria. So mesophilic bacteria will survive within 30 to 40 degrees temperatures. Methanogens will work low at 12 to 15 degrees. So it will not be suitable for colder regions. Methane will not form. So tropical countries like India can use anaerobic digestion system, but colder region cannot adapt to this technology because methanogens will not produce any methane if it is less than 12. Another factor is nutrient. So as I mentioned, nitrogen to phosphorus ratio will be optimum at 7, and the COD to nutrient ratio, that is nitrogen ratio, will be 350 by 7. Optimum COD nutrient, that is nitrogen ratio will be 400 by 7. 400 by 7, that is around the 60. Okay. So for one nitrogen, 60 carbon need to be there. But in aerobic system, very less can also be like one part, that is 30 is enough, I guess, in aerobic. I mean 30 carbon, one nitrogen is enough. But here 60 carbon will be taken care by one nitrogen. So that's why we are adding 1 lakh COD also. The anaerobic treatment can treat. That's the good thing with the anaerobic treatment system. But it also requires some trace minerals like molybdenum, selenium, tungsten, and nickel necessary for the sustainable enzyme activity because all the enzymes will produce with these nutrients. Then volatile fatty acid inhibition. We need volatile fatty acid. Then only acetate will form, acetic acid. Then only methane will form. But some will inhibit this VFA here itself, so the methane production will not be there. What are the problem? Slow growth and sensitivity of the methanogens. Accumulation of organic acids decreases the performance of the reactor. If the methanogens are not performing well, VFA will stay in the system, will again reduce the pH. So VFA concentration maintained below 500 milligram per liter. Otherwise, preferably you can maintain at 200 milligram per liter for optimum performance. Otherwise, acetic acid will considered as it will reduce the pH and it will affect the performance of the system. Acetic acid is the least toxic acid, but propionic acid is the highly toxic that will affect the performance. There are two acids, acetic acid. I mean, two acids that will be present in the system. One is high toxic, one is less toxic. Acetic acid will be less toxic. Propionic acid will be highly toxic. It will have a impact on the performance of the system. Then ammonia nitrogen inhibition, as I mentioned, NH3, NH4 plus will form with instead of acetic acid to methane, acetic acid will also produce ammonia. So that will be a problem. But high ammonia concentration generally causes rapid production of VFA. Again, this will produce volatile fatty acids. Then again, it will produce acid that will be reducing the pH, reducing the methanogenic activity. Why? Methanogenic activity requires 5 to 8.5 pH. But here, acids forming lesser pH. Then sulfide inhibition. Oxides of sulfur get reduced to sulfides. Sulfur containing amino acids may undergo degradation to form sulfide with the help of sulfur bacteria like sulfovibrio. That is a kind of bacteria that will oxidize the sulfur to sulfides. Again, H2S will be forming. H2S is a harmful gas again with the biogas. Then heavy metal inhibition, copper, nickel, lead, chromium, if it is present in the wastewater, microbes will die. So that is the problem with the heavy metal inhibition, performance inhibition by the heavy metals. That induces toxicity to the anaerobic bacteria. And the characteristics of anaerobic treatment process are low biomass yield. As I mentioned, low biomass, only 5% sludge only will be produced. So that is a good thing. Low biomass yield compared to Arabic. Arabic produce 45% biomass. So that will be settled in the secondary settling time. Then fewer nutrient requirement. But why the anaerobic produce only 5%? Because slow metabolism of microorganisms due to absence of oxygen. Then fewer nutrient required, less biomass production, so only less nutrients is required. So 60:1 is also considered good optimum. For wastewater lacking sufficient nutrient, the cost of nutrient addition is much lesser than the anaerobic process. No nutrient addition, no oxygen addition, that and all reducing my cost of the treatment. Then high volumetric loading rate. As I mentioned, 1 lakh milligram also I can add. So high volumetric organic loading rate. Organic loading rate and small reactor is required, less space is required. So that are all advantages. Organic loading rate of anaerobic system will be 3.2 to 32. But here compared to 0.5 to 3.2 only for aerobic. So that is very less. Here higher volumetric loading rate. Then operational condition like longer startup time is the problem, sensitivity is the problem, operational stability is the problem, adder is the problem, corrosiveness of the digestive gas because that will be H2S, CO2, this kind of gases will be very corrosive to the reactor. So the reactor inner surface will be corroded. And need for alkalinity addition. Why? Because the VFA production will reduce my pH. So I have to add some buffer like ammonium bicarbonate, sorry, sodium bicarbonate or calcium carbonate. Then only I can make it into 5 to 8.5 pH for the methanogens to grow. Also maintain acceptable pH for high gas phase CO2 concentration. The need for further treatment. So whatever the biogas produced with the CH4, CO2, H2S will not be pure. I want only the methane having high calorific value. So I have to remove all this. So some post-treatment is required for biogas, also for the effluent, because effluent contains 5 to 15% of the incoming COD. So that is a problem again. So I need to treat the effluent again. But it is good only. I can use this as a preliminary treatment, primary treatment, then I can use the aerobic treatment followed by. See, that's what mentioned here. How can I apply the system? It's significantly concentrated wastewater I can use, more concentrated water. With large COD, I can use anaerobic treatment system. it is not adaptable for municipal wastewater because it's having less biodegradable, less COD. I need more COD or more BOD. Then only the system will work. And the industrial wastewater are much higher biodegradable COD concentration. So I can use this system for industrial wastewaters like slaughterhouse waste, sugar industries, distillery industries. This type of industries will have high COD concentration wastewater. I can use the anaerobic treatment system. There I can put aerobic treatment system with lots of oxygen supply. Okay, so anaerobic process can be used for high COD concentration than desired, but advantage of using anaerobic system in the first stage than using aerobic system in the second stage or any advanced treatment. So that will work out. So I have 1 lakh COD in my wastewater. I am using anaerobic treatment system. So that will reduce 85% and only 15% will come out. That is 15,000. Then this less concentrated wastewater I will use aerobic treatment system with the aeration tank and all. Again it will reduce to 90%. So 15,000 90% will be like 9 plus some 13.5, right? 13.5 will be removed, only 1.5 will come out. So that will be my whole treatment. I can use this as a pre-treatment. For which industries, like all industries having large organic matter, I can use alcohol, each production, wine production, potato processing, coffee industry, fruit, fish, vegetable industries, I can use the system. Okay, whereas the types of anaerobic treatment reactor systems, there is a high rate and low rate. High rate will be of having less solids like 4 to 10%, like biogas settlers, ABR, AF, USBR, some of the examples of high rate anaerobic treatment system, low solids. But here, low rate, low rate in the sense with the biomass retention time is very less. HRT will be very less considered to sludge retention time. But here, HRT will be equal to SRT, so low rate. There is the slow movement of water. So here, slurries we can use like wet digestion and dry digestion are the two types of low rate. Like PFR, CSTR are some examples of wet digester. For dry digester, I can use anaerobic biogas digester. There are again types of this with wet digestion and dry digestion in the low rate system. Whenever I'm having high, yes, hello. If you have any doubt, you can ask. You can unmute and you can ask, or you can put.
Hello. Hello.
Yeah, please.
Yeah. So I want to just ask one thing that is not related directly with this. So whether high BOD by COD ratio is most suitable for anaerobic treatment, or low BOD by COD ratio is suitable for anaerobic treatment.
No, low BOD by COD ratio will not be suitable for biological treatment system first.
Okay.
So after that, aerobic or anaerobic is based on high BOD. I mean, uh, what like high strength BOD or high strength wastewater and low strength wastewater will be based on aerobic or anaerobic system. You got it. Per
Okay.
1 lakh or 1,000. If you compare 1 lakh COD and 1,000 COD, I can choose aerobic for 1,000, anaerobic for 1 lakh. That is high strength wastewater, low strength wastewater. But in the 1,000, if only 10 is biodegradable, then I can't use any of the system because biological treatment system will only work with the biodegradable organic matter. So BOD should be always high, nearly that is a ratio called BOD by COD. Sorry, COD by BOD ratio will be should be greater than zero point 0.4. That means it should be nearly equal to 1. Then only 0 0.4 to 1 I can use the system, the biological treatment system. Yeah, I hope it's clear. Let me move on. So again, anaerobic reactor systems are classified into conventional treatment and high rate system. So high rate will be HRT will be equivalent to SRT. So that's a, sorry, less than SRT, and HRT will be equivalent to SRT for low rate anaerobic digestion systems. Again, there is a classification similar to aerobic system, like disposed growth or attached growth. The microbes are suspended in the system or attached to the system. Then attached growth again classified into fixed bed, rotating bed, expandable bed in the anaerobic system. But in aerobic system, how we are classifying aerobic, whether it is suspended or attached growth. Then whether it is okay, that's it. Yeah, that's it. So suspended AFP is one of the example. Attached growth, rotating biological contactor, that is the example. Okay. Yes. So one of the best example of anaerobic digester is UASB. UASB are again becoming popular in most of the industries and for municipal wastewater treatment systems. So upflow anaerobic sludge blanket reactor. So the name itself indicates what is the process happening in this. UASB, upflow anaerobic sludge blanket. So the water is coming from bottom to top. That's why it's called upflow. Okay, anaerobic, again it's closed, there is no supply of oxygen, so that is the anaerobic. Sludge blanket, all the sludges are settled at the bottom, so the water is flowing through the sludge, so if passing through the sludge blanket, that's why it's called upflow anaerobic sludge blanket reactor. You got it? And the pure water is coming from the top. Biogas is also from here. Biogas is also collected at the top. Sludge will be retained at the bottom. Water will be coming through from the bottom. You got it? So that's the reactor. So it is developed by Netherlands scientist Professor G. Lettingia in 1970s. Upflow anaerobic sludge blanket reactor. It's a single tank process. There is no need of any settling tank because settling is happening in the same tank. And most popular anaerobic wastewater treatment across the world. And it is used for industrial wastewater treatment. So see the reactor. It's kind of settling tank only. A hole contains sludge. So this is called a sludge zone or settling zone. Sorry, sludge blanket zone. Sorry, blanket zone, sludge zone. Then this is the inlet zone. First is the inlet zone. Second one is the sludge blanket zone. Third one, after passing through the sludge, the water will start. The solids in the water start settling. So that is called a settling zone. This is called a settling zone. And pure water will, because after passing through this, there is no solids in this. All the solids are settling. So this is a clear zone or gas liquid solid separating zone, because here clear water will be there. I have a gas collector, it's a closed tank. So gas will come out, water will flow through this, solids will go down. So this is called gas liquid solid separator zone, GLSS. All three phases of materials will be separated in this tank, in this zone. Finally, out zone. Okay, so inlet zone contains from bottom to top, that's why upflow. Sludge blanket zone, all the sludge will be there as a blanket kind of thing. Allow this, the reaction is happening in the sludge blanket zone. All biochemical reactions are taken in, the degradation is happening in this zone, anaerobic degradation. Then, after reaction, the gas will be produced going up, and the water will be moving through this. Some will be settled, water only will move out through the effluent zone. So that is called the settling or clarifying zone for the solid settling. Then finally, gas liquid solid separator. Collect the gas, solids push it to the settling zone, water flows through the effluent pipe of the chamber. Finally, one more component is that is the deflector. See, there is a triangle zone here. So all the gas will be touching this deflector and moving here. And all the solids will touch this deflector and come down. You got it? The movement of solids will be through gravity. The movement of air is also through gravity to the top, and only the pure water will come out through the system. So whatever crosses the funnel will come out as the effluent, pure water. You got it? So water centers from the bottom and flows upward. Suspended solid blanket will degrade. All the reactions will happen at this blanket zone, and 5% will be converted into biomass and again settle. Only 75% will be, sorry, 45% will be of biogas and treated water. 80% will be biogas and treated will contain some 5% of waste. 15% of COD will come out again. Upflow regime and the motion of the gas bubble allows mixing. There is no mixer or mechanical rotator here. The bubble itself acts as a mixing zone. You got it? The upflow bubble and the motion of the gas bubble allows mixing through the mechanical assistance. And then finally the separation will happen as the GLSS phase. This is the design criteria for a typical UASB reactor to handle 15 to 10 to 15 mld of sewage. So I can use 4.5 to 5 meter depth of the reactor. The length is required, or diameter also you can choose. Sludge blanket of out of 5 meter, 2 to 2.5 meter will be my sludge blanket. Another 2.5 will be my clarifier zone and settling zone. And settler compartment, finally HRT I have to maintain, SRT I have to maintain. After 30 to 50 days, I can take out the sludge and the sludge will replenish. That's what sludge retention time. Whatever the sludge is going out for 50 days, that will be the accumulated sludge, 5% accumulation. Then gas production will be, this is very important, 0.38 meter cube of biogas will be produced per kg of COD. So if I have 1 lakh milligram per liter, then how much 1 lakh milligram per liter? Then if I convert milligram to kg, gram, another kg, 1 kg per liter of COD is coming. So that will produce 0.38 meter cube of biogas. Think about 1 meter cube. Out of that, 1 by 4 will be my biogas. Sorry, 1 by nearly half is my biogas. So that much biogas is produced with 1 kg of COD itself. So that is very important value, 0.38. Then gas utilization, 1 meter cube of biogas with again this 1 meter cube of biogas contains 75% methane. That 75% will be giving 1.4 kilowatt hour of electricity. So I am using this. So USB
Sir,
same, yeah.
sir, what is meant by HRT and SRT, sir?
How much time the water is staying in the system, wastewater is staying in the system. Sludge retention time is how much time the sludge is retaining in the system. That is, the water will see what is the time for HRT, 8 to 10 hours. So water will take 8 hours to cross this point to this point. So that is the hydraulic retention time. How much time the water is retained in the system. Sludge retention time is how much time the sludge is there before coming out of the system. So that is the sludge inlet and outlet point also there. So out for 50 days the sludge will be retained in the system and it will come out. But in the ASP, if you see, all the sludge will be taken out in the settling tank and it will be replenished again. SRT will be very low for ASP system, but here it will be very high. So the water is also staying for a longer time. Here it will be in 1 hours, 1.5 hours, but here it will be 8 hours, 10 hours. So high COD will be reduced in anaerobic system. You got the concept? Yeah. Yeah. Let me continue. If you have any question, please ask or post it in the chat box.
Shall you do any numerical for this part?
Simply this my milligram conversion will have. I'll explain. Yeah. So again, the same anaerobic advantages will be there for UASB also, like high reduction of BOD or COD, low sludge production, because 5% will be sludge, and biogas can be used for energy, no aeration system, effluent is rich in nutrient, low land demand, and reduction CH4 and CO2 emission will be reduced. All will be taken care by the biogas system. But the problem is treatment may be unstable. It will not give us a steady output. Requires operation and maintenance by skilled laborers, long startup time. The anaerobic bacteria need to be adapted to the system. A constant source of electricity is required, requires expert design, effluent and sludge required for the treatment, because 5% sludge, whatever settled, needs a treatment, and the effluent also have 15% COD, that also needs another treatment. And then not adapted for colder regions, as I mentioned. Temperature required for the methanogens is 30 to 40 degrees Celsius. So that will be adapted only in the tropical countries. And UASB can be applicable for large scale industrial wastewater treatment, high organic load rates, like 10 kg BOD per meter cube per day. If that much high load, this UASB can be used. But because it's having less low land return, it cannot be used for low strength wastewater that contains too many solids, like fats and proteins, or like municipal solid waste. We can't use UASB. UASB is not proper for small or rural community without a constant water supply or electricity or skilled labors. You got it? Yeah. Some more other types of anaerobic treatment systems like anaerobic contact presses, upflow packed bed, downflow packed bed, and fluidized expandable bed we are going to see. See, anaerobic contact process. Here, similar to ASP, we are having a tank, closed tank that will have a feed, that will have a mechanical system to rotate. Gas will be collected at the top. After treatment, because it's a mixed system, I will take some time in the sedimentation tank to settle the sludge. You got it. So this is called anaerobic contact process. So whole microbes will always be in suspension and it will be in contact. It's a stirred tank. You got it. It's a stirred tank. UASB is not a stirred tank. The bubble will mix the system. But here we are mixing with the paddle. And the biomass leaving with the reactor effluent is settled and recycled, increasing SRT, and biomass separation may be improved in this contact process, and concentrated waste containing refractory suspended matters. A continuous and complete mixing is not recommended, so we are having a separate sedimentation tank for the sludge to settle. Otherwise, if we are mixing more, sludge will not settle. If you are mixing less, dead zone will form. So then the mixing need to be optimized. You got it. So that's the optimization required in the anaerobic contact process. It can be suitable for industrial wastewater treatment. Then anaerobic filters. Here it uses a packed bed. Similar to upflow anaerobic reactor, there is a system with a packed bed. So this contains the anaerobes. So or any naturally crushed materials like plastic, ceramics, this kind of materials will be filled. Microbes will be sticking towards the surface of the filter materials like ceramics or plastics having higher specific surface area and porosity. Through in the pores, all these microbes will be attached towards. Finally, a number of such filters we have constructed for treatment of low strength wastewater municipal solid waste. Why? Because I am having only less BOD like municipal solid waste and all. That cannot be go in contact with the microbes, so I have to use this type of special media that is suspended in the system to make it into contact with the anaerobic wastewaters. Then anaerobic fixed film reactors AFF. This have microbial mass immobilized on the fixed surface. There the beds are moving like moving bed bioreactor in the aerobic system. Here the bed is moving. The inert materials are moving. Here the anaerobic bacteria are fixed to a material like a refractory particulants that will after some time all the microbes will grow and it will be sloughed out. The film biofilm layer will be taken out and it will be going along with the effluent, discharged along with the effluent. That may be submerged or unsubmerged condition. This bacteria, this holder or any kind of like supporting media. Okay, this consists of plastic sheets providing a high void ratio. Treating high strength wastewater, this will be suitable. If you see in the picture, see there are lots of sheets. In the sheet, microbes will be attached. Water will be flowing. When it come in contact with the sheet, it will be taken care. Here, packed bed, all the plastic media containing what we say microbes will be suspended. Water will go through this and it will come out. Finally, we have fluidized bed reactor FBR. So here it will incorporate upflow reactor partially with sand, coal and plastic bead. This will have again a larger surface area, but the flow is upflow. Okay, system readily allows passage of particulate plug a packed bed, and here the bed will get expanded. Do not aim at complete fluidization, but it will start expand and it will lower down with the flow velocity. We can maintain the depth of the the sludge zone with the flow velocity. The reactor can be used for treatment of municipal solid sewage as well, because we can reduce the sludge zone, we can increase the sludge zone. If we are using for high COD removal, we can increase the sludge zone. That kind of we can use this fluidized bed. Finally, come to the biogas part. What can we do with the biogas that is captured? All the sludge and the biogas will be like this biogas production will be common throughout the country, but biogas collection is rare. Production of biogas is common, but collection of biogas is rare. Why we are not collecting how much biogas we are producing from agriculture is 68%, landfill gas is 12%. See, these are all related to environment. We are collecting 12% of biogas from landfills and 7% of biogas from wastewater treatment. Others are commercial, residential, and agricultural. But this why we are not using or capturing this biogas for energy production, because methane recovery and purification is a cost intensive process. We have CH4, CO2, and H2O. I need to remove this. That is called the purification of biogas. I need only the methane. So that will not happen. 70% is this, 30% is this. So how can I treat this 30%? That will again cost intensive process. So methane production is common, but methane utilization is not common. That's why many places methane is simply flared. Whatever the biogas coming out, that will be simply flared. If you see some of the long chimney having fire at the top in the wastewater treatment plant or somewhere, if you see our landfills, they will flare the biogas. Why they are flaring? After flaring, CH4 will be converted into CO2 and emitted into the atmosphere. If you simply emit the CH4 into the atmosphere, there is a higher potential of greenhouse gas compared to CO2. CH4 is 24 times higher greenhouse gas potential. So I should not simply let the methane out of the system. So I will flare and convert it into CO2. See the graph between oxidation state of carbon and the composition of digestion gas. If I use -4, -2 oxidation state of carbon, like fatty acids, I'll produce more methane, less CO2. If I use urea, oxalic acid of high +5, +2, +4 oxidation state, I will have 25% methane and 75% CO2 only will come. So to get more CH4 and less carbon dioxide, I have to I have to use the less oxidation state carbon sources. Similarly, if you see how much biogas will be produced for how much COD TOC ratio, if most all of them are COD, then it will become higher. That contains larger methane production. That's why COD should be more to get a higher methane production. If you see formic acid and oxalic acid, carbon will be more, organic carbon will be more, but COD will be nearly similar to that. That will produce lesser methane production. And another formula, this is very simple formula, that is a Duolingo formula. If you use any organic matter, CHO, A and B as any, if you take glucose, C6H12O6. So N will be 6, A will be 12, B will be 6. Okay, so CnHaOB, it will react with the H2O and produces CO2 and H2O, sorry, CH2 and CH4 as a product. How much water is required, how much CO2 will be produced, how much CH4 will be produced, we can calculate with this empirical formula. That's the modified Duolingo formula. You can use the same table you can adopt for 1 mole of CH4 is equivalent to 64 gram. We know the molecular weight, right? So the amount of CH4 produced will be 0.4 liter methane per gram of COD. So if you think about 1 kg, it will become 400 liters of methane. Any doubts, sir?
Sir, what is meant by empirical formula, sir?
What is mean by?
Empirical formula.
Empirical formula are the one, what we can say, it will have some numbers in this, like if I think 683 O2 plus 92 N equal to gives some numbers, numericals will be there, plus 1 by 9, plus 1D. If you this kind of numbers are there, I can't multiply or reduce any values in this system. So that is the empirical formula. If you derive like BOD, we have derived like LT equal to L naught into e power minus KT. This is not an empirical formula. I can multiply 2 here, I can multiply the same 2 here. I can multiply 3 here, same 3 I can multiply here also. That will not affect my equation. But if you think about empirical formula, that is derived from trial and error experiments, and they have formed the equation like 365N plus 16O2 plus 1N plus 6B by 2. So here I should not add any 2 anywhere, because that will not give me methane production, right? So this is, for example, I am saying this equation. So if you can't alter anything in this equation, it should be the same number everywhere. Here I can use the 3LT equal to 3C L naught into e power minus KT I can use, but here I can't use that, because plus will be there, minus will be there, that will have some numbers in this. Why? How these equations are formed? They will use different N, different O, different S with the different organic matters, and they will calculate the CH4 production in experiment basis. After hundreds of thousands of experimental trials with the values of CH4 produced, they will use some of the software to form the empirical equations. Like right, in the mathematics ODE, based on the, differential equation, they can arrive at this type of particular integral and characteristic factor to frame this empirical equations. Yeah. So empirical equations are the one you have to use the same numbers everywhere. That's it. That cannot be altered. That's based on trial and error experiments. But when it comes with the derivation, then it is not a empirical formula. It's a derived formula. I can derive it anywhere. This is not derived from anywhere. You can't derive this equation. It is based on the experimental value. But this is derived value with the from a graph or logarithmic graph. I have derived this equation, right? Yeah, that's the difference. So this you can use as a simple formula for calculating how much methane you will get when you are using any organic matter. So how can find the organic matter formula? If you have any wastewater, you give to CHNSO analyzer, it will give you how much C, how much H, how much N, how much S, how much O. So that you can convert into any formula. C365, H12, N6, SO, S3, O1. Like this, I can frame the empirical, what do we say, molecular formula of organic matter. Okay. So if you know this, substitute in this formula, you will get the methane production. So that's it about today's lecture. We have discussed about the basics of anaerobic treatment. What are the advantages of anaerobic treatment over aerobic treatment? Um, and phases of steps of anaerobic process: hydrolysis, acetogenesis, methanogenesis. 4 stages of organic anaerobic process. Then we have discussed about uh, upflow anaerobic sludge blanket reactor, UASB reactor. Then some other types of anaerobic treatment system we have discussed. Okay. So can we move on to the problem solvation?
Sir,
Yeah.
sir, actually, I has been get a mail from your end. Sir, tomorrow will be also a class. Is it there, sir?
I'm sorry. What you got the mail from?
Tomorrow will be also conducting classes.
Tuesday. I'm not conducting any class tomorrow. Maybe the other PMR scholar. Actually, we are having 3 PMR scholar for the same course. Saturday 68, Monday 68, and Tuesday 68. I am taking every Monday 68. So every week that's happening.
Sir, in Tuesday we don't have class, sir.
No.
From Tuesday.
My class will be every Monday 68. The other PMR scholars will take every Tuesday 68 same course. Last 7 week he is also taking every Tuesday. Yeah. Let me move on to the problems. I will read the problems. You please post the answers in the chat box. Which of the following is not required in an effective anaerobic reactor used for wastewater treatment? Sludge wasting, aeration, pH control, gas collection. So the name itself indicates it's an anaerobic reactor. What is anaerobic? It will not require oxygen. So oxygen is not required, which is not required. Aeration is not required. Sludge wasting, anyway, we are doing 5% sludge we are getting, that we are discarding. pH control we need to do because volatile fatty acids are producing. We need to add buffer. What is buffer? Buffer is the one which will maintain the pH. So if it is an acid, I will add alkaline buffer that will maintain at 5 to 8.5. And gas collection, biogas will be produced in the anaerobic system, so I need a gas collection. So all these 3 are required. Which is not required? Aeration is not required in anaerobic process. You got it? Moving to the second question. Please post the answer in the chat box. In an anaerobic treatment of wastewater, methane is produced from initially long chain fatty acids will be converted into short chain fatty acids. Then it will be converted into acid COO minus. Then it will be converted into CH3COO minus. Then it is converted into methane. But here itself it will be having CH2. So H2 will also produce CH4. Acetic acid will also produce methane. Similarly, we will also get methane from the same acids, volatile fatty acids what we have produced. So the first will be the long chain fatty acid that will be converted into the short chain fatty acids. From the short chain fatty acids, we will get the um, volatile fatty acids. So the volatile fatty acids will reduce the pH of the system that will be converted into acetic acid. From the acetic acid also directly methane will produce. From the acetic acid H2 will produce. From the H2 CO reaction will be H2 plus CO2 that will also produce CH4. So here the question is the in anaerobic system wastewater methane is produced from both acetic acid H2CO2 also from other acids. So all the above will be the answer. You got it? So the reaction you have seen in the slide number 12 anaerobic system, the last step that is the methanogenesis step that will produce methane from all these pathways. You got it? So if you have any doubt, please let me know. Yeah. So I'll move on to the next question. So VFA is produced in anaerobic digestion refers to. What is VFA? So here there are four steps in the process. First is hydrolysis, methanogenesis, hydrolysis, acetogenesis, methanogenesis. You got it? So in the acetogenesis, volatile VFA will be produced. VFA means volatile fatty acids. VFA. So the answer is A, volatile fatty acids. You got it here? So initially high molecular weight will be converted into low molecular weight. Here the low molecular weight will be converted into intermediate compound. That is the VFA. VFA will be my intermediate compound. Propanoic, butanoic acids or any acids formed will be of volatile fatty acids. So here they are asking about the optimum pH for methanogenesis to reactor. So as I mentioned, anaerobic system will be highly pH dependent. There are lots of factors that will affect the anaerobic system will be sensitive to lots of factors like pH, time, temperature. So all that will affect my system. So pH will be reduced when VFA is produced. But again, the fourth step is methanogen that requires 5.5 to optimum range will be to 8. I need to maintain. So here the option will be 6.5 to 6.6 to 7.6. That is the optimum range for methanogenesis bacteria. But non-methanogens is 5 to 8.5. So here we have to use 6.5, 6 to 7.6 for methanogenic bacteria, and what I have written is for this is for non-methanogen. So methanogen requires 6.6 to 7.6. How can I maintain 6.6 to 7.6? I'll add some buffer to make the volatile fatty acids pH to 6.5 to 7.6. You got it? So please remember this value. It will operate at the neutral pH. Methanogens will operate at a neutral pH, that is 7. Okay. Now, complex proteins and carbohydrates are converted into amino acids and sugar via. So protein and carbohydrates are long chain fat. High molecular weight organic compound, organic matters. Amino acids and sugars are low molecular weight organic matters. That is soluble organic matter. This is unsoluble. This is soluble. How this is happening? With the reaction with the enzymes. How the enzymes are formed? From the microorganism. So microorganism cannot digest all the organic matter. So the high molecular weight organic matter are initially converted into low molecular organic matter by the enzymes produced from the microorganism. Then it will digest the simpler organic matters. You got it? So this process is called hydrolysis. Here, long chain organic matter will be converted into like a simpler organic matters, and like OH is produced. You got it? OH from the high molecular weight with the addition of water and enzymatic activity. This process is called hydrolysis. Hope you are with me. If you have any doubt, please let me know. Okay. Here, there are two statements given. First is, relatively rapid assimilation of anaerobic microbes leads to shorter startup times of anaerobic reactor compared to aerobic reactor. So they are saying anaerobic reactors requires shorter startup time compared to aerobic system. Is this correct? No, because anaerobic system requires a larger startup time. That is a disadvantage. Then second statement is due to high metabolism rate in the absence of oxygen, anaerobic system have higher biomass yield. That is also wrong because I am having only 5% of biomass yield. That is the sludge because it is having less metabolism rate. I am having higher HRT, high SRT, so less metabolism rate, less yield. That's why sludge is very less. So that's my advantage. So both these statements are incorrect. See, low production of solids, 5% lower than aerobic system. So that is the advantage. And another one is here. What is the other question? Shorter startup time. That is, the process will be very slow due to larger startup time. That is a disadvantage. So both the statements given there are wrong. Okay. Then seventh question. Heavy metal present at high concentration is an anaerobic reactor may lead to. What are the problem with pH, time, temperature we had seen? Similarly, ammonia, like sulfide reduction and heavy metal will have problem. Like heavy metal, what will create? It will accelerate the process. No, the process inhibit due to inducing toxicity. Like small metals are required, like selenium, molybdenum are required for the anaerobic reactors too. That is very negligible amount is required, trace element. But this type of heavy metals like cadmium, chromium, nickel, arsenic will have effect on microorganism that will inhibit the enzyme activity. You got it? So heavy metal always inhibit the enzyme activity of the microbes. So it will reduce the that will induce toxicity and reduce the production. High production of biomass is wrong. Rapid increase in the pH is also wrong. Heavy metal don't have any react with the pH. Here, see. Heavy metal inhibition, copper, nickel, lead, chromium present at higher concentration will induce toxicity in the anaerobic reactor system. Moving on to the 8th question. The UASB reactor is typically not suitable for treating. All anaerobic system will be working with the high strength wastewaters, right? High strength wastewater like industries. Why we are not using for domestic or municipal wastewater? Because this contains more dilution, less strength wastewater. We will say this is a less strength. Hardly it will be 1000, 2500 COD will come. But here 1 lakh, 10,000 leachates will be 1.5 lakh industries are producing. So that kind of wastewater we can use UASB. So high strength wastewater we can use. Low strength wastewater we can't use. Domestic sewage contains densely populated, so that will be again high strength. So that is this both we can use. Low strength we can't use. So the answer is which is not suitable. Low strength is not suitable. You got it? Yeah. So influent with low cost strength containing too many solids, then UASB will not work properly. It will work good for large scale industries or the population, the rural or small communities with a high population. Match the system here. As I mentioned, there are 4 steps in the anaerobic digestion process: hydrolysis, acidogenesis, acetogenesis, and methanogenesis. What will happen in hydrolysis? All the high molecular weight organic matters OR will be converted into simpler compounds like OH. So this will be correct. Acetogenesis, this OH will be converted into acetic acid. So this OH, all the VFAs will be converted into COOH. In methanogenesis, methane will be formed. From acetic acid, methane is forming. Or from anything methane is forming, then it is called methanogenesis. So answer is C, A, B. So C is correct. Correct. You understood the equations here. OR is converted into OH. Then whatever production will be COOH is produced, then COOH is produced, CH3COOH is produced, acetic acid is produced, and finally from this CH is produced is one type of methanogen. Yeah. 10th question is with the UASB. In upflow anaerobic sludge blanket reactor, which of the following components facilitate effluent outflow nearly free from solids and gases? In UASB, there are 4 zones, right? What are they? So if I draw like this, inlet zone from the bottom. This is sludge zone or sludge blanket. So the first one is inlet zone, second one is sludge blanket. Here solids will start settle. That is settling zone. Water is coming in. So this is third one, settling zone. Fourth one is clear zone. Water will go out. Here this is the GLSS, fourth one. GLSS, that is gas, liquid, solid separator. So gas will go through this, effluent will go through this, solids will go down. So they are asking which component facilitated effluent outflow nearly free from solids and gas. So the top will be facilitating this reaction. The top will be GLSS. So gas, liquid, solid separator will separate 3 phases. Gas will be collected, solids will be pushed out, and the clean water flows through the effluent pipe. So that facilitates, GLSS facilitates. Got it? Got the 4 parts of UASB? Yeah. So 11th question is, which of the following is an anaerobic treatment system that does not require inert media? So we have seen lots of types of anaerobic reactors. So which does not require inert media? Upflow anaerobic sludge blanket. Whether we used any inert media here? No. So this is correct. Anaerobic filter. In anaerobic filter, we need lots of plastic sheets. In fluidized bed reactor, we need a plastic media or sand media. Sand media, it will flow like a sand. Anaerobic fixed film, again we need a plastic media that will be fixed. The anaerobics are fixed on the surface. That requires high surface area inert media are required. So all this requires inert media. But UASB, what we had seen earlier, will not require any inert media. So the question is, which not requires any inert media? Upflow anaerobic sludge blanket reactors. UASB reactor. UASB. Okay. Then 12th question. Here comes the numerics. Sir was asking about some of the numerics. So we will solve some simple unit based numerics. See, UASB reactors are, we are given with a UASB reactor designed with a 6 mld wastewater. So it's coming from any city or a industry. 840 milligram per liter of COD is coming within this 6 mld. So the Q is 6 mld. Okay. What is the COD? The pollutant range or substrate is 840 milligram per liter. Okay. At a volumetric loading rate, volumetric organic loading rate, VLR will be 24 kg COD per day per meter cube per day. With the unit, see, this is million liter per day, so liter per day into 10 power 6 I can add. Okay, this is milligram per liter. So if I divide the, if I multiply this to 6 into 6, 10 power 6 into 840, I'll get liter will get cancelled. Milligram per day will come. You got it? With this milligram per day, I have 24 kg COD per meter cube. So I can get how much meter cube of treatment is happening. Assume that 1 kg of COD produce 50 gram of biomass. What is 1 kg? 1000 gram, right? 1000 gram of COD will give you 5 gram biomass, that is the sludge or the bacteria. 800 gram biogas, that is the mass balance. So directly mass is converted. So how much is remaining? This is not 5 gram, 50 gram. 50 gram biomass, 800 gram biogas. So remaining is 850. So 150 is my, this is the inlet BOD. So 150 will go out. So that's the effluent COD. You got it? Based on the information, the required effective volume of the UASB. They are asking about the volume. So volumetric loading rate is giving E meter cube. So I can divide and get it. So 6 into 10 power 6 into 840 milligram per liter. If I divide it with the 24 kg per meter cube per day. So this day will cancel kg. If I convert again to milligram or this m power 6 if I divide 6 into 840 by 24 will be my meter cube volume. See, correct or not? 6 into what is the answer? 6 into 840 by 24. 210 is the answer correct? Yeah, 210 meter cube is correct. This is correct. So just a unit calculation only. Okay, simply you can cross multiply, you will get. Yeah.
Why you take 24, sir? You know,
Sorry, can you repeat?
you actually get confused on why you take 24, and the sense of question is given. That's
Yeah, something is given as 24 only, right? Volumetric organic loading, right? 24 kg COD per meter cube. Again, I will tell you for this. See, the Q is 6 mld. That is 6 million liter per day. You got it? Then they given inlet COD or COD load as 840 milligram per liter. So, volumetric organic loading rate is 24 kg per meter cube per day. So they are asking what is the volume of the tank. So I need in meter cube. So with this, if you find how to find meter cube, so this should be divided. So I will get the meter cube. So if you multiply this two, I'll get liter will cancel 840 into 6 into 10 power 6 milligram per day I will get. So if I divide this two, day will get cancel, milligram and kg will get cancelled, meter cube will come. You got it? That's why I divided 640 into 6 into 10 power 6. Then 10 power 6 I will convert milligram to kg. So directly I can write kg per day and divide it by 24 kg per day, meter cube will come out. So that's the answer. If I cancel it, 210 meter cube will get. That's the volume of the tank. You got it?
I got it.
Yeah. So 24 is given in the question. Yeah. Here, the same question they are asking, what is the COD of the treated effluent? What is the COD of the treated effluent? 1000 gram la, that is 1 kg of COD inlet la, 50 gram is biomass, 800 gram is biogas, then 150 gram is my effluent COD. Oh, sorry, 150 gram per kg of COD. But my inlet is 840 milligram per liter. So if you multiply this, I will get C. 1 kg produces 150 COD in the effluent. So what is the efficiency? 85% removal efficiency. Only 50% is coming out. So what is my COD in the system? They are asking what is the COD of the treated liquid, treated effluent. Yeah, here if you see, COD in the treated effluent is 15% of inlet 840. I'll get 126 milligram per liter as my, because 150 gram per 1000 gram into 840. If you multiply, you will get 126 milligram per liter as the effluent COD. The third question is, assuming 60% of methane content in the biogas. So they are producing 800 gram, 1000 gram, 5 will go out as sludge, 15 will go out with the effluent, 80 grams is converted, 800 grams will be converted into methane. So that methane, biogas, that biogas contains 60% as methane, another 40% as CO2 or something, H2S and all, small amount of trace gases. So they are asking, density of the methane is 465 kg per meter cube. The daily production of methane, what is the daily production of methane? Out of 840 milligram per liter, out of the 840, how much percentage? 5% gone, 15% gone. So 80% is biogas. In the 80%, 60% is my methane. So I will get some milligram per liter. Multiply 840 into 0.8 into 0.6. I'll get 403.2 milligram per liter as biogas. And then methane. I need in meter cube. So if I divide by 465 kg per meter cube, again this is in liter, this is in meter cube. So I'll convert it into 1000. 1000 will go up, and milligram to kg. Kg will again 1000 into 1000. So only 1000 will be there. So 403.2 divided by 465 by 1000. Again, that will give me meter cube. Everything it can get cancelled. Only 840. Okay, I did forget to multiply the cube because we need the 6 million liter per day. So how much liter per day of 840? So 6 also there. 6 million liter. 6 million liters are also there. So if I have see multiplication, everything I will show here. Out of daily biogas production, 800 grams are producing per 1,000 grams. That is 0.8. Out of this 5040 is my daily COD in. That is the multiplication of Q and inlet COD. Or you can also again multiply 6 into 10 power 6 into what is the inlet COD? 840. If you multiply again, you will get the same. In this 4032 kg of methane I will get per day, but they are asking in terms of meter cube. They given the density also. So this out of this biogas, 60% will be my methane, and for 465 meter cube per kg per meter cube will be my density. So if I convert everything into meter cube, you will get 5.2 meter cube per day. Let me clear everything and do with the question itself. 6 into 10 power 6 into this is liter per day into 840 milligram per liter. If you cancel, you will get milligram per day. This much COD is coming in. Out of this, I have converting 80% as biogas. Out of the biogas, 60% is my methane. Then if you divide, this is in milligram per day. Then if you divide it by 465 kg per meter cube, you will get the answer. And convert this milligram into kg again, it will get cancelled. So the answer is 6 into 840 into 0.8 into 0.6 divided by 465. I'll get 5.2. Yeah, this is correct. 465. You are getting the answer. 6 into 8.840 into 0.8 into 0.6 by 4. Why 0.8? Out of 1 kg, 800 gram is biogas. Why 0.6? Out of 100 biogas, 60 is methane. Then why 465? To convert the kg of methane into meter cube of methane. You got it? If you have any doubt, please ask me. This much water, this much COD. So the total COD is this much. Out of this much COD, 80% will be converted into biogas. Out of this much biogas, 60% is converted into methane. Out of this much methane, I will convert it into meter cube. That's the logic. Just multiply with the unit, you will get the answer. Final question is, in a UASB reactor, same question, the daily sludge production. How much sludge is produced? 50 gram is biomass. So 50 gram, that is 5%, right? Out of 1050 is 5%. So 5% will be my sludge production. See again the same 6 into 10 power 6 into 840. Out of this much COD, 5% will be my sludge. In terms of kg, they are asking. So cancel the 10 power 6. 6 into 840 into 0.05. 252. The answer is 252 kg per day. So per day I have to dispose 250 kg of sludge, right? If you think about aerobic, 45% is my sludge. So multiply the same question with the 45%. 6 into 840 into 0.45. I have to dispose 2262 kg per day. Think 2200 kg of sludge. Think about 252 kg of sludge. How can I dispose? That's the
So where
particular.
you are getting the 5%?
See, 1 kg, that is 1000 gram. Only 50 gram is my biomass. That is the sludge.
Okay, sir.
So 50 by 1000 is my 5%. That's what out of 1000, 550 is going, that is 5%. 800 is going as biogas, that is 80%. 15% is my effluent COD. Yeah, that's the answer.
Okay, sir. Thank you.
Yeah. So just another 10 question, small recap. A primary constituents of biogas. They are asking about biogas, the produced biogas. How much will be methane, how much will be carbon dioxide, and how much will be other gas? 70% will be my methane, 30% will be carbon dioxide plus other gas. So 3C is correct. This is the typical constituent of a biogas. See, everywhere it's mentioned 75% as methane. Another 25% as CO2. That will be in the range of 17 to 30. Yeah. Which of the following is likely to be a major disadvantage of anaerobic wastewater treatment process compared to aerobic process? Disadvantages of anaerobic. Lower removal of nutrient pathogen. Yeah, that is one major problem. Higher land requirement. No. Anaerobic process occurs with less land because only one tank. Lower functionality under high organic load. That is also wrong. High organic load, it will perform good. So, lower nutrient removal efficiency and pathogen removal is my problem. See, unsatisfactory removal of nitrogen, phosphorus, and pathogen is a disadvantage of anaerobic system. But that will be an advantage of aerobic system because I am putting lots of oxygen. I am sending for some more time. Then all the nitrogen will be extended aeration system. This type of nitrogen nutrient will be removed. Yeah. Think about the third question. What is the phase? Match the first numbers with the phase, the order of anaerobic process. So first step will be hydrolysis. Second step will be acidogenesis. Third step will be acetogenesis because acid, as all the acids will be converted to acetic acid. Fourth step will be methanogenesis. Okay, here. So answer is B, D, A, C. This is correct. Yeah. So these are all steps of anaerobic digestion. Yes. Then anaerobic degradation, the formation of acetic acid, which first VFA will be produced at acidogenesis. Acetic acid will be produced at acetogenesis. Got it? Answer B is correct. Got the answer? Yeah. Fifth question. The component of COD that are typically not removed by the anaerobic degradation. So what we had, a total COD, out of total COD, some are recalcitrant, COD recalcitrant, some are soluble or biodegradable, BD. Out of this this recalcitrant will not be degraded, so it will come as it is. And out of biodegradable, some will be converted into cell mass, COD cell. Some will be converted into volatile fatty acids. Again, out of this volatile cell will come as it is, it will not do anything. Recalcitrant will come as it is.
ప్రపంచంలో టాలెస్ట్ బిల్డింగ్.
Sorry? Hello? You want to ask?
Sorry, you can proceed.
Yeah,
You can proceed.
Yeah, I will proceed. Out of COD volatile fatty acid, some will stay as it is, COD volatile fatty acid. Only some volatile fatty acid will be converted into methane. You got it? Or biogas. So this biogas and the cell will go out of the system. The recalcitrant will come along with the effluent and some VASA. So what the question is, which is not removed? Recalcitrant COD is not removed. Biodegradable organic matters are removed. COD from the particulate matter, that is also removed. All that will be converted into volatile fatty acid, right? So one is not removed, that is recalcitrant COD. That's what given in this figure. Recalcitrant will always come out as it is. Yeah. What is recalcitrant? Which is organic only, but not biodegradable organic. What is the example? Some plastic organic only. Some wood that's containing lignin, which is hard to degrade by the microbes. What else we can say? Textiles are organics but cannot be degraded. You got it. This type of smaller fragment that can be soluble also, but not degradable. Typically, the least toxic volatile fatty acids are like we have like volatile fatty acids. We have two types. One is like lots of types are there. Highly toxic is propanoic. Low toxic is acetic acid. That's why all the bacteria are adapted to acetic acid and they will convert it into methane. Right? We have lots of acids, volatile fatty acids, but high toxic is propionic and low toxic is acetic acid. That's why they are asking least toxic volatile acetic acid. Right? See, acetic acid is considered as the least toxic, whereas propionic acid accumulation is considered as a problem for anaerobic reactor. Yeah. I cannot say like high toxic, but it will affect the system. Another two statement. An increase in the ammonia concentration cause rapid production of volatile fatty acids. Yes, because ammonia will give you CH3COH or any acid it will produce. That is correct during the anaerobic degradation. VFA causes a decrease in the pH. Yes, whenever acid is formed, volatile fatty acid only, right? A is acid. pH will reduce, leading to reduction in the methanogenic activity. Why? Because methanogens will work only with the 6.6 to 7.7 or 7.6. That nearly that 7 range only it will work. When if pH is reduced, methanogens will not produce methane. So both statements are correct. Right? Yes. High ammonia accumulation, rapid VFA, decrease in the pH, reduction in the activity. That's the linked process. UASB reactor is an appropriate example of. I have discussed about high rate, low rate. What is high rate? HRT will be less than SRT. In low rate, HRT will be equal to SRT. SRT will be nearly in months. HRT will be in days in anaerobic systems. Or sorry, not in days, in hours, 8 hours, 10 hours, like that. So UASB is a high rate anaerobic, but suspended or attached? Suspended only. If there is no inert material to attach, right? So UASB is a high rate anaerobic suspended growth only. You got it? Why it's a high rate? That the PPT will show. Let me once. Sorry, 1 second. Yeah, here. If you think about the example of high rate anaerobic, UASB is one of the example. High rate anaerobic suspended only, right? It's suspended, yeah. Okay. Let me go through the next question. The biochemical reaction in the USB reactor majorly occurs in the. We have 4 zones of the USB. Again, let me go through. First is inlet zone, second is sludge blanket zone, third one is settling zone, fourth one is GLSS zone. Gas, liquid, solid separator zone. Right? So the biochemical reaction will happen. Where the reaction is happening? Whenever the microbes is there, reaction will happen. Where the microbes are more? In the sludge blanket. So here the reaction is happening. So all the biochemical reaction is happening at sludge blanket. You got it? So that's the answer. Biochemical reactions are taking place at the sludge blanket zone. Settling will happen at the clarifier zone or settling zone. The effluent will be taken out, clear effluent will be separated out at the GLSS zone. Water is getting in at the inlet zone. That's the four zones in the UASB. Identify the incorrect statement of anaerobic treatment. They are asking first is uh, heavy metal and sulfates may act as a potential inhibitor. That is correct. Whenever heavy metals and sulfates are there, that will affect the system. Lesser nutrient requirement is primary advantage of this process. That is correct. We don't want to add nutrient because nutrient will not be removed. That is correct. The major drawback of the process is the portable production of foul smell. Probable production of foul smell. Yeah, that is also correct because foul smell will be the problem with the anaerobic system. The organic carbon in the wastewater is entirely converted into sludge. That is wrong. Only 5% is converted into sludge. 80% is converted into biogas. 15% is converted into 50% will go out along with the effluent when 100% COD is coming in. So it is a typical range. 80% will be converted into biogas. That's a good thing. Only 5% is the sludge. So option D is incorrect statement. Yeah. Adequate mixing of UASB is facilitated by, in the UASB what I have drawn, is there any mechanical device to rotate? No. Then how mixing is happening? The bubble that is produced, that will have a mixing effect, right? So adequate mixing in UASB is facilitated by upflow regime because water is always in agitation when I am supplying the water from the bottom, right? So it will be in a vibration. Upflow regime and gas bubble formation. The gas bubble will move here and there. That will again mix the water. Whenever instead of aeration, the gas that is bubbles that is produced in the system will what we say will mix the system. So the mixing in the UASB is facilitated by upflow regime and gas bubble system. Here it's given. The upflow regime and the motion of the gas bubble allow mixing without mechanical assistance. We don't have any mixer. But in the other system, we have a mixer, paddles and all. An anaerobic reactor that requires inert media for operation is all the above. Contact process requires, filter requires inert media, fixed bed requires the media, all requires, right? See, extended tank reactor requires here, sorry, not the extended tank. Area, some plates are required. Yeah, parallel plates, separators are required. Naturally crushed rocks or plastic materials are required. Inert materials are required. Here, fixed surface is required for the immobilizing the bacteria, right? Only UASB not requires any media. Which of this is not a component of UASB reactor? Four zones we have discussed, right? Settling zone is there, sludge blanket zone is there, solid liquid gas separator is there, GLSS, yeah. Aeration zone is not there because UASB is an anaerobic reaction. Aeration will not happen, will not require. So aeration zone is not there. See the question. In the process of biogas production, glucose is converted to CO2 and methane. What is glucose? C6H12O6. Okay. It is converted into, if it is aerobic, then CO2 and H2O will form. If it is anaerobic, CH4 and CO2 will form. How to balance? 6C are there, C6 are there. So here C3, here 3. Okay. 3 to 6 O are there. So here 3, 4, 3 are 12 are there. Okay. So this is anaerobic microorganism. There is no oxygen. Anaerobic. Okay. 85% conversion efficiency. Not all are converted into methane. 85% is converted into methane. Methane gas produced in the reactor is 25 with a 25 mld. Q equal to 25 mld. They are asking methane gas produced. How much methane gas produced in meter cube? Having a COD, glucose is a COD, right? So 200 milligram liter is my COD or glucose concentration. 200 milligram per liter. Assume the density of methane as 465 kg per meter cube. They are saying 25 million liter per day into 200 milligram per day. So milligram will cancel. Okay. Out of this 85% conversion. So how much? 0.85 will be converted into methane. And then out of this divided by 465, what I will get? Milligram per day. but I need in kg. So this, if we cancel kg per day, so if you divide it with the kg per meter cube, then meter cube per day I will get. So 25 into 200 into 0.85 divided by 465. I'm getting 9.1. But the same 200 into 25 divided by 465 and all correct. This I forgot. The molecular weight I forgot. They given the equation, right? So we need to convert the glucose molecular weight to methane molecular weight. How many moles? 3 moles of methane. 1 mole of glucose is converted into 3 mole of methane. How much the molecular weight of glucose? 180. 180 is the molecular weight of glucose. What is the molecular weight of methane? 12 plus 4, 16. So 1 mole of 180 gram of glucose gives 3 moles of 16 gram of methane. So 3 into 60 divided by 180. So what I am getting the answer into 3 into 16 divided by 180. If I put answer is 2.43. Yeah, 2.437. That is correct. What I got is the COD, but they are asking about the methane. So if I convert this into biogas, then convert the same COD into glucose terms. So I will get in this equivalent. 180 gram equivalent will produce 16 gram equivalent into 3.
So please you can report in the conversion of units to the understand.
Okay, let me do again. So as I mentioned, 180 gram of glucose, 1 mole of 180 gram of glucose will give you 3 moles, because C6H12O6 gives 3 CH4 plus 3 CH4, CO2. So 3 moles of 16 gram of methane. So how much I will get from this much COD? So that will be 3 into 16 by 180. Okay. Into what I have discussed earlier, 200 mld, that will be again converted into kg into 25. This is kg per day. This is meter cube. Liter per day, how much? Liter per day, milligram per liter. Yeah. This is milligram per liter, liter per day. So liter will cancel, kg per day. Again, kg you have to convert into meter cube. So kg per meter cube is my density, 485. That is 465. That is they did in the next step. Always MLD you convert, million always you will take out liter per day. Again milligram per liter, liter will get cancelled if you multiply simply. Then divided by whatever given in the kg per meter cube. Then whatever milligram or kg will get cancelled. Only meter cube will be there. Meter cube will come up, meter cube per day. You got it?
Got it.
Yeah. So another question, 15 mld wastewater. Okay, that is the Q or discharge or inlet. Okay, containing 10,000 COD. So COD is 10,000 milligram per liter. Results in 78% COD removal. So 78% removed. Only 22 is coming out along with the effluent. Okay. Stoichiometric calculation suggests that 1 kg of COD produces 50 gram of biomass. 50 gram of biomass. 50 gram is 5% only, right? 1000 gram la 50 gram is 5%. Determine the amount of sludge produced. So, out of this much COD, 10,000 milligram per liter, Q is 15 into 10 power 6 liter per day. So how much milligram per day I am giving to the system? 10,000 into 15 into 10 power 6. Out of this, 5%, 0.05 will be my sludge. If you want to convert into kg, because the answer is in kg, take out the 10 power 6. So 15 into 10,000 into 0.05. 15 into 10,000 into 0.05. What is the answer? 7,500. Then conversion is again 0.78. So again 0.78 if I multiply 5850. Yes. Because COD reduction is 58, COD removal efficiency is 78%. So 0.78 also I will multiply. So if you convert this 70, where it is answer. 1 liter of wastewater contains 7.8 gram of COD. That's what given. Yeah. 1 kg of COD reduction, 50 gram of biomass. 7.8 into 50 by 1000 equal to 0.39 gram. If you just do my calculation, it will be very easy for you. 10,000 will give you 0.05 is the production out of 15 mld. 15 into 10 power 6. Again, it will be cancelled kg per day. I want again 0.05 is my sludge production. Removal efficiency is 0.78. So if you multiply everything, 15 into 10,000 into 0.05 into 0.78, I will get 5850 kg of biomass. Out of treated system only, I will get the biomass. So you have to multiply 0.78 always. Here 0.05 and 0.78 are efficiency only, not having any unit. 5%, 78%. This will have only the unit. So final answer will be kg per day. They are asking determine the amount of sludge produced in the reactor per day. So 5850 kg. So that's it for today. Thank you so much for joining the 7th week of session. If you are registered for the examination, please don't forget to give the assignments on time. Wednesday end is the deadline for every week's assignment. We will meet next Tuesday 6 to 8 for the 8th week session. Okay. Thank you all. Thank you for joining.
Sir, I have the,
Yeah, please.
sir, we are upload to 7th week answer solutions.
So, sorry, you have?
Sir, are you upload 7th week solutions?
Solutions.
I'm asking about.
No, 7th week assignments for this week, actual assignment you are asking?
7th week solution, 6th week, sir. I'm sorry for that confusion.
6th week answer you can see in the portal itself, right? See, I'll show you. No, I will not upload actually. The NPTEL team will do that. I am just assisting the system. You can see that here.
Yes, sir. Sixth week answer is already uploaded.
Yeah, already uploaded. You can see here.
Yes, sir. Yes, sir.
Yeah,
By
yeah.
logging, we can see.
By login, you can see. And my lecture material, you can see here. Let me show you that also. So you are asking about last week solutions quiz. You see the answers are uploaded. Yeah, the answers are given. Accepted answers, the correct answer, everything is given.
So, but I'm asking solutions. So some of your numerical questions is there.
Solutions. Okay, that actually I will discuss in the 13th week. I have one more special session after 12 weeks. We have 3 weeks time for the examination maybe. So that time I will take after the 12th week I will discuss all this 12 weeks problems. Okay, solutions and all.
Thanks.
Yeah.
Thanks, sir.
So my session you can see here problem solution recordings. If you it will be redirected into a Google Sheet. There first column will be mine. The other 2 PMR scholars lecture also you can see in these videos. So I have uploaded 6 videos and 7th week video today I will upload here. Then like the material you can see in this drive. Lecture material what I have discussed and the problem solving PPTs everything you can see here. Okay. So if you have any doubt please let me know.
Thanks for guidance, sir.
Thank you so much.
Nothing.
If you don't have any doubt, you can leave the meet. Thank you all. Okay, let me close the meet. Thank you for joining. We'll meet next week.